Hello and welcome to all my young friends who are studying in intermediate and they are watching this video. Welcome to Calculus Made Easy series. In our last videos, we have discussed and completed the topic of limits. Today, we are going to start a new topic, and the name of the topic is continuity. But before we start our new topic, let us just have a quick recap on what we have learned till now. We have discussed that in calculus, we deal with the study of continuous change. And if you want to study the change, we have to establish a relationship between different variables, and the function is a special kind of relationship where for each independent variable there is only one dependent variable. Ca- Calculus is mainly devoted to the study of functions and limits, and there are certain checks for a function. The first one was limit, continuity, and the third one differentiability, but differentiability we'll be discussing in the later videos. Today we are going to discuss continuity. So what do we mean by continuity? It's simple. What we mean in our daily life, the same meaning uh, is there for continuity in calculus. So that means a function is said to be continuous if it can be drawn without picking up the pencil. Suppose we are drawing the function that is its graph like this. We are not picking up the pencil, but if we draw like this and there is a gap, so here we need to pick up pencil, or there is a jump, so here also are required to pick up the pencil. So both these are discontinuous function, where this is a continuous function. That is what we mean by continuity here. So we can also define it that a function is continuous if its graph has no holes or breaks in that. So let us see certain examples. The curves of continuous functions can be like this. See, this is a straight line, this doesn't have any gap, or it can be like this. Examples of discontinuous functions can be, suppose the line is coming till here and then there is a gap, so this is a discontinuous function. Or the curve is coming like this and then there is a jump, so both are the cases of discontinuous function, whereas these cases are continuous function. This is our depiction by graphical method. Say we are drawing the graph of function, but if we want to establish it mathematically, that means what should be the mathematical condition for a function to be continuous, right? Now there is a figure graph of a function y is equal to of x in front of you. If I ask a question, is this function continuous, everybody of you will reply no. Why? Because there is a jump. That means right hand limit will be c1, and if you approach from left, the limit will be c2. That means right hand limit is not equal to left hand limit. Function is discontinuous. Okay. Another function is depicted here. The right hand and left hand limits both are equal to c. Is this function continuous? You will say no. Why? Because right hand limit and left hand limits are equal, but there is a gap. There is a very small gap. In fact, it's a very small gap. I have to show it bigger because I can't depict a point. It's a point gap. At x is equal to, say, a, function is not defined. So although both the limits are exist and they are equal, limit exists at a, but still function is discontinuous. How to make this function continuous? How should I make it continuous? So can you just guess it? If you fill this gap, you put one point here only, you require to put only one point here. It will make it continuous by filling the gap. So how to fill the gap? By filling the gap means, since at A the functions is not defined, so if the value of function at A becomes equal to the right and left limit, then means the gap will be filled. That means the right hand limit and left hand limit, both which are equal to C, they should also be equal to value of function at A. Gap will be filled. So function becomes continuous. Now, for a function to be continuous at A, at x is equal to A, say, first it should be defined at A. Second, limit must exist. That means right hand and left hand limit should be equal, and both these limits should be equal to the value of function at A. That means fa should be equal to fx a plus fx a minus limits. That means fa is equal to the limit of the function at x is equal to, because limit x tending to a fx means that limit exists, which you can say either right limit or left limit. So we can also write this condition in this form, that fa should be equal to the right limit or left limit, or we can just write fa should be equal to limit of fx at a. That itself means that both the right limit and left limit are equal. What is the condition for a function to be discontinuous? Discontinuous if one or both the two limits fail to exist. If they do not exist, gone, it is discontinuous. If they exist but still they are not equal, then also the function is discontinuous. Third, they exist and are equal but not equal to f, then also function is discontinuous. That means the function is continuous when its limit exists at that particular value of x and is equal to the value of function at that point. Now we come to one theorem, very important theorem. If there are two functions fx and gx which are continuous at x is equal to a, both these functions are continuous at x is equal to a, then the following functions are also continuous at x is equal to a. That means fx plus gx, fx minus gx, fx into gx, some constant c into fx or some constant c into gx, where c is a constant belonging to real number, or fx upon gx, या gx upon fx, provided this is not equal to 0 at a. That means fx upon gx, where ga is not equal to 0, yeah, or gx upon fx, where fa is not equal to 0, means denominator should not be equal to 0. So that means if there are two continuous functions, there is some difference product of you multiply any function by a constant or their quotient, provided your denominator is not equal to 0 at that particular value of x, that is a, then these functions are also continuous at x is equal to a. This is very important theorem, although it seems very simple, but very, very important theorem. So let's do some examples. We are asked that there is a function fx is equal to 2x plus 1, where x belongs to real number. We have to test its continuity at 0. What will we do? Simple. We will see left hand limit, which is equal to f 0 minus h, limit h tending to 0, which is equal to limit h tending to 0. So put 0 minus h in place of x. That means 2, 0 minus h plus 1. Now if you put the value of h as 0, it comes to plus 1. The right hand limit, this is equal to limit h tending to 0, f 0 plus h, limit h tending to 0, 2, 0 plus h plus 1, that is also equal to plus 1. So right hand limit is equal to left hand limit, and f0 is equal to 2 into 0 plus 1 is equal to 1. So left hand limit is equal to right hand limit is equal to f0. That means function is continuous at x is equal to 0. This is quantity at x is equal to 0. Now we'll also see by drawing its graph. Function is y is equal to 2x plus 1. That means minus 2x plus y is equal to 1. X upon minus half plus y upon 1 is equal to 1. This is a straight line which has an intercept of minus half on x-axis and 1 on y-axis. That means it passes from here and this point. So this is a straight line. You can see it's very clear from this graph that this is continuous at x is equal to 0. Not only at x is equal to 0, but for all real numbers, this is continuous, right? That means fx is equal to 2x plus 1 defines line without any break. Hence, it is continuous at x is equal to 0. Let's see another example. Fx is equal to x square minus 1 upon x minus 1. So we have to test its continuity at x is equal to 1. Now, right hand limit is equal to f 1 plus h, limit h tending to 0, which is equal to limit h tending to 0, 1 plus h whole square minus 1 upon 1 plus h minus 1, which is equal to limit h tending to 0, 2h plus h square, because 1 will get cancelled and here we'll be remaining with h. So h will get cancelled, limit h tending to 0, 2 plus h, because this h will get cancelled here. That means limit is equal to 2. Left hand limit is equal to limit h tending to 0, f 1 minus h, which is equal to limit h tending to 0, 1 minus h whole square minus 1 upon 1 minus h minus 1, which comes to limit h tending to 0, minus 2h plus h square upon minus h. So minus h will get cancelled and it will become limit h tending to 0, minus 2 plus h, which is equal to, plus 2 minus h, right? So this is equal to 2. So right hand limit is equal to left hand limit. But f1 is equal to 1 square minus 1 upon 1 minus 1. That means this is equal to 0 upon 0. So this is an indeterminate form. So right hand limit is equal to left hand limit, but this is not equal to f1. That means this function is discontinuous at x is equal to 1. And we can also, see its continuity by drawing its graph. Now, how to draw the graph? Y is equal to x square minus 1 upon x minus 1. You can write it x minus 1, x plus 1 upon x minus 1. Now x minus 1 gets cancelled only in case when x is not equal to 1. If x is equal to 1, this will be 0 and this will be 0. You cannot cancel in 0 in numerator and denominator. You can only cancel when x is not equal to 1. So y is equal to x plus 1 only when x is not equal to 1. For x is equal to 1, it is not defined. That means minus x plus y is equal to 1, x upon minus 1 plus y upon 1 is equal to 1. This is a straight line which has an intercept of minus 1 on x-axis and plus 1 on y-axis, and except x is equal to 1, this line is defined everywhere. So this line will come like this and have a gap at x is equal to 1 and then proceed from there. So you can see that there is a gap here at x is equal to 1. That means fx defines a line with a break at x is equal to 1, hence discontinuous at x is equal to 1. The third case is we have function fx is equal to 1 if x is less than or equal to 0 is equal to minus 1 when x is greater than 0. So we have to check its continuity at x is equal to 0. So our left hand limit is equal to f 0 minus h limit h tending to 0, which is equal to 0 minus h means less than 0 comes in this region 1. So it's a constant value. The right hand limit is equal to limit h tending to 0 f 0 plus h. So it comes in this region greater than 0. So that means there is a constant value minus 1. We don't need to find the limits. So LHL is not equal to RHL. Although the value of the function at 0 is equal to 1 because function is 1 if x is less than or equal to 0. So now although LHL is equal to F0, but this is not equal to RHL. That means function is discontinuous at x is equal to 0. Now if you draw the graph, y is equal to 1 for x is less than or equal to 0 and y is equal to minus 1 for x is greater than 0. That means if x is less than 0, y is equal to 1. This is a straight line which is parallel to x-axis and at a distance of 1 from x-axis. That means this line, and this line terminates till x is less than or equal to 0, only till this place. And from here, when x is greater than 0, y is equal to minus 1, which is again a parallel line to x-axis, but it cuts y-axis at minus 1. It starts from this place. So you can see clearly this is also a discontinuous function, because if you draw this function, it defines a broken line with break at x is equal to 0, hence it's a discontinuous function. So for all these three cases, for first case we saw that RHL is equal to LHL is equal to F0. So this was continuous function. And the second case, RHL was equal to LHL, but this was not equal to F1 because at 1 it was undefined and it was discontinuous. Then for the third case, LHL was not equal to RHL. Although the value of LHL was equal to, this was equal to F0, but it is a discontinuous function. So from all these three examples, I hope that you are clear with this idea of continuity. So let's solve some problems so that we get more clarity on this topic. So let's quickly do some questions. First question says that function fx is defined in three regions like this, and we are required to check the continuity of the function at 1 and 2. So you can see at 1 and 2, the definition of function is changing. So let's check at 1 at x is equal to 1. So what do we need to check for continuity? We need to check the left hand limit at 1, the right hand limit at 1, and the value of the function at 1. These three should be equal, then only the function will be continuous. Now, f1 is equal to x is less than or equal to 1. Here, function is defined as x plus 1. So 1 plus 1 is equal to 2. The right hand limit is equal to f1 plus h, limit h tending to 0, which when x is greater than 1, it comes in this region, that is limit h tending to 0 to 1 plus h, which again is equal to 2. So the value of function at 1 and right hand limit both are 2. Let's see what is our left hand limit. Is equal to limit h tending to 0 f1 minus h. When x is less than 1, the function is defined as x plus 1. So 1 minus h plus 1, limit h tending to 0, which is equal to 2. Now right hand limit is equal to left hand limit is equal to value of the function at 1. So function is continuous at x is equal to 1. Now let's check at x is equal to 2. At x is equal to 2, the value f2 function is defined as 1 plus x square. 1 plus 2 square, that is 5. Right hand limit at 2 is equal to limit h tending to 0 f2 plus h. That means greater than 2 function is defined as 1 plus x square, limit h tending to 0, 1 plus 2 plus h whole square, which is equal to again 5. Left hand limit is equal to limit h tending to 0 f2 minus h. So 2 minus h is in region less than 2 and function is defined as 2x. Limit h tending to 0 to 2 minus h. So this equals to 4. That means right hand limit is not equal to left hand limit. And although right hand limit is equal to f2, but this values is not equal to left hand limit. So this all three should be equal to discontinuous. So let's see what is the answer. Continuous at 1 and discontinuous at 2. Let's see second question. Here we are being asked as to what is the value of k for the function to be continuous. Now this function is divided into two parts. One is y is equal to 2. Now y is equal to 2 or y is equal to k square x minus k. So this is a straight line, this is a straight line. Both are continuous functions. So that means we have to check only at 1. If it becomes continuous at 1,